The
Good morning.
students, they can't wait for more than.
Yeah.
Sorry, that's
Yeah. Good morning, everybody. I extend warm welcome to our beloved principal, Dr. D. Hanumantarao Garu, and today's speaker, Dr. Mithun Polith, scientist of DMRL, HODs, and faculty and students to today's webinar. Being organized by Department of Science and Humanities under the able guidance of our principal, this webinar is being conducted on the occasion of National Science Day. And on this day, India's prominent scientist, Sir C.V. Raman, invented its famous theory, Raman effect, on 28th February 1928, for which he was awarded Nobel Prize in the year 1930. So, yesterday also, we have started celebrating this National Science Day, and yesterday we have conducted quiz for the students of BE first year. And today we are conducting the guest lecture by the scientist from DMRL. And I now request our honorable principal to address the audience. Sir, please.
So, good morning, all. First of all, my best wishes on the occasion of Science Day.
Thank you, sir.
So, it's good to organize by the Science and Humanities department. And the response for yesterday quiz also very overwhelming. So, more than 300 students participated.
Right.
And those who got successfully completed, they got the certificates also.
Yeah.
So, as a part of that activity, so today Dr. Mithun sir is going to deliver a lecture on materials. So I hope every student whoever is online right now and watching through YouTube channel will get benefited and have some kind of a knowledge upgradation, especially in the materials front. I hope the seminar will go on very well and will add value addition to each one of you are participating after completion of today's activity. So once again, thank you. I thank personally Dr. Mithun sir for accepting our invitation to address our students and faculty and for sharing your knowledge on materials front. So thank you one and all and have a nice day. Thank you, sir.
Thank you, sir. Thank you very much. So before I invite today's speaker to deliver the lecture on the materials for defense applications, I now request Dr. M. Srilata, Assistant Professor of Physics, to introduce today's speaker, Dr. Mithun sir, to the audience. Madam, please.
Thank you. Thank you, sir. Can you hear me?
Yeah.
Yes, madam.
Thank you, sir. Good morning, one and all. I am Dr. M. Srilata, Assistant Professor of Physics, Sciences and Humanities Department, Mathrusri Engineering College. I take the pleasure of introducing today's eminent speaker, Dr. Mithun Polith. Sir has completed his PhD from Indian Institute of Science, Bangalore in 2013. Sir worked on structural and microstructural attribute on magnetostriction of terbium, dysprosium, iron, and iron gallium alloys. Sir has worked as a guest scientist at Institute of Nanotechnology, Germany. Currently, Sir is working as a scientist F, Advanced Magnetics Group, Defense Metallurgical Research Laboratory, DRDO, Hyderabad. Sir has published more than 55 research articles in refereed journals. Sir presented his papers in more than 100 national, international conferences. Sir has received INSA Medal for Young Scientist in 2014, awarded by Indian National Science Academy. Young Metallurgist of the Year Award in 2010, awarded by Ministry of Steel, Government of India. DRDO Young Scientist Award in 2009, awarded by Defense R&D Organization. IIM Student Prize in 2003, awarded by Indian Institute of Metals. Indranil Award in 2003, awarded by Mining, Geological and Metallurgical Society of India. University Medal in 2002, awarded by Bengal Engineering College for securing first rank in DE. Sir has delivered several invited lectures in various national, international conferences, workshops, and training programs. Sir has elected as a core committee member in Indian National Young Academy of Science, which is the Young Science Council affiliated to Indian National Science Academy. Sir is a life member of Indian Institute of Metals, Materials Research Society of India, and Magnetic Society of India. This is the brief introduction of today's speaker, Dr. Mithun Palik, sir. Now I request sir to take over the session to enlighten our students on materials for defense applications. Thank you, sir. Over to HOD, sir.
Okay. Thank you, madam. Thank you very much. I
Thank you,
now
sir.
request today's speaker, Dr. Mithun College Garu, to deliver his lecture on materials with applications in defense. Sir, please, Mithun sir.
Yeah, may I share my screen now?
Yeah. You can, sir.
Can I see?
Yeah.
Are you seeing? All?
Yeah. It is.
So, thank you, Dr. Srilata, for such a nice introduction. And I thank Honorable Principal and Honorable Head of the Department, SNH, and also the event organizer from the Matrusri College of Engineering for giving me this opportunity to talk to all of you regarding what we are doing at Defense Metallurgical Research Laboratory in Hyderabad. So basically, I understand from the brochure shared with me by Pawan that you are looking for, it's a series of webinar on the defense materials. And today I will be talking about one of the very important material, functional material, which goes to different defense systems, which is permanent magnets. And I understand that I will be speaking to a diverse audience. Therefore, I will touch upon first a brief theory of this permanent magnet, and subsequently I will talk about certain application, certain processing, the complexity, the challenges of this class of material. Well, today's
excuse me, sir. Sorry for interrupting you, sir. Can you make it full screen, sir?
I have made already. I have made it full screen.
Slideshow, sir. Slideshow.
I have made it slideshow already. Is it not coming as slideshow?
It's not coming like that, sir.
Okay, 1 second. Let me. Is it okay now?
It is showing same, sir.
Wait a second. So maybe I should stop presenting and start once again.
Yeah, better, sir.
Yeah. You please try that, sir.
No, sir. No, sir. Actually, you use Alt tab. You will find that screen. Full
Okay.
screen. Slideshow screen. No, once you check.
First, I should go full screen and then all.
Alt tab. You just click. You will find that window. Full screen window.
It is showing same, sir.
Slideshow screen has to be selected.
Yeah.
I should stop presenting and start once.
Or else you do that. Sir.
Yeah. I will tell you.
No, sir. No, sir. Actually, you use
Yeah. Is it visible now? Full screen?
Wait, sir. It is loading, sir.
It's okay?
So same thing, sir. Again, it is not full screen.
Okay. So in that case, what I will do, I will maybe But is it scrolling? Is it scrolling if I go to the next slide?
Yes, it will go, sir.
Can you see my next slide? I have already gone to next slide.
It is showing first slide only, sir.
Okay, so then I think maybe
Yeah,
we
it is
have
showing
to
second
go.
slide now. It is showing second slide now.
Yeah. I think better I will go this mode, so that will be easy actually. Okay.
Okay, sir.
So today is also a very special occasion because it is National Science Day, which is we always cherishly celebrate the birthday of the great scientist, Nobel laureate, Dr. C.V. Raman. And I must say that C.V. Raman, although he is famous for his Raman effect, he has a very great footprint in the field of magnetism, because there are certain liquids which is having magnetic property and certain organic molecules. The magnetic properties and anisotropies of those molecules was detected using the Raman spectroscopy. In fact, Dr. Raman also has published some of his work during his lifetime. So as I must impress upon the gathering today that magnetism is very magnetic. You know, when we call someone a magnetic personality, means he always attracts people around him or her. And magnetism as a field of study is having such attractive features, and it attracts people from different disciplines, engineers, scientists, I think electrical engineers and electronics engineers, mechanical engineers for some design of certain system, and of course the material scientists and physicists. So it is a thoroughly interdisciplinary field that we will understand as we progress with my talk. So magnetism is a phenomenon which is there everywhere around us. Whether we understand it or we don't understand it, we always experience or we always encounter several things with respect to magnetism. And magnetism has lot of economic potential. It has several hundreds of billions. Of course, this figure shown here is quite old. I'm sure it has gone many fold by now. The magnetism in the nature is also coming from, because you see that whenever there is a lightning during thunderstorm, this lightning will actually induce magnetism in some of the natural rocks called lodestone. This is basically iron oxide based rocks. So under the influence of lightning, they get magnetized. And also the earth's magnetic poles, they have interaction with the electrical particle comes from the solar discharge from the sun, and they create some kind of a colorful features in the sky in the polar region, which is called aurora borealis. So therefore we can see nature also manifest several things related to magnetism. This is the chronology, the timeline of different invention of magnetism. Actually, the name magnet came. There are, of course, it has happened in a place called Magnesia, where a shepherd, when he has a boot with a nail, and when he was going with his herd of the sheep, he found one fine morning that the nail of his boot is getting attracted to some kind of the rock. And from the name of the place, Magnesia, where the rock was first found, that the entire the substance which was catching, which was attracting the nail, was named as the magnet. And since then there are several inventions, and the first invention, some device related to magnetism, was compass, followed by several other theories, and finally today we are talking about molecular magnets or the nanomagnets. So the field has traveled a lot actually. So magnetism, what we call, is the force of attraction or repulsion between the magnetic materials due to its particular atomic arrangement, which is arising from its certain electronic configuration. And this origin of magnetism can be any moving charge, whether it's an electron which is orbiting around the nucleus or a current carrying conductor, they always create the magnetic field. And this current carrying conductor's magnetic field is utilized in several ways, which we are seeing in different devices and different applications in our day-to-day life. In fact, the Earth is also having a magnetic field because the core of the Earth is having this liquid salts, liquid oxides, and there are a lot of ions, ionic species present in the core of the Earth. And we all know the Earth spins around its own axis as well as it rotates around the sun. During this rotation, that liquid metal which is there in the core of the Earth, their charge is mobile, and accordingly this is behaving like similar to a current carrying conductor, and that is why the magnetic field comes from in the Earth also. So magnetic materials, if I look at element wise, there are very few elements actually shows magnetic properties. Mostly iron, cobalt and nickel, these 3D transition metals, and amongst the rare earth gadolinium, they are only magnetic or technically called ferromagnetic at room temperature. And this, as I mentioned in one of my earlier slides, that the magnetic property comes because of the electronic configuration. I will illustrate it in this slide. For example, let us take iron. So iron has the 3D orbital of the iron, the 3D shell that is having not completely fulfilled. Therefore, we can see the iron is ferromagnetic. And you take another transition metal, copper. So if you take pure copper, then what we find that the D3D shell is completely filled. So there is no unpaired electron in this 3D shell, and thereby these behave as the diamagnetic, whereas any ions of the copper, for instance, copper 2 plus, where the electrons, the 3D shell is not completely filled, and thereby it has some kind of the unparalleled electron, and thereby it shows paramagnetism. Of course, it is ferromagnetic at lower temperature, and at room temperature or ambient it is paramagnetic. Well, when we start about the magnetism, we should start from a current carrying conductor. What we see here, a solenoid. Inside the solenoid there is a material, and we are sending current through the solenoid. When we are sending current through the solenoid, by virtue of the flow of electron through this coil, there will be some magnetic field which is along the axis of the coil will be generated. And when it is generated, and if we have a ferromagnetic material placed inside the coil, it will also have some orientation of the magnetic domains. Again, I will come what are there, and this orientation will contribute some of the magnetic fluxes, and together they will form the magnetic induction B. So magnetic induction has two components. One is H, which is coming from the external electron what we are sending inside the coil, and other one is M. M is the inherent magnetization which is contributing to the flux when the external magnetic field is applied. So, therefore, this is a very basic equation of the magnetism, that B equal to H plus M, or if we consider the relative permeability, and then it is a mu zero term comes over here, and the material, how strongly they are magnetic or how weak they are magnetic, is decided by a term called the susceptibility. So susceptibility chi is the ratio of M divided by H. M is the magnetization of the material, and H is the applied field. And therefore, based on these susceptibility values, there are 4 different types of magnetic material. One is paramagnetic materials, and it's ferromagnetic, that is iron, cobalt, nickel. They have a definite Curie temperature where they lose magnetism, and after that Curie temperature, when they are magnetic ordering, that is all the spins they are oriented parallelly. So when they lose this order beyond the Curie temperature, then they becomes randomly oriented spin, and they call paramagnet. There are, of course, some other type of material where there are the two spins. You can see they're anti-parallel to each other, and this type of material are called antiferromagnetic material. And antiferromagnetic material, sometimes they have one lattice spins not completely neutralizing the other lattice spin, and those material will have a weak magnetism at room temperature, so they are called the ferrimagnet. And antiferromagnetic materials also undergoes ordering. This kind of perfect ordering of the two spins in the opposite direction happens at temperature below called the Nil temperature, and beyond this Nil temperature they again become haphazardly oriented like a paramagnetic material. These are the basic terminology one should know to understand to understand the magnetism and the related phenomena. So they are remanence, coercivity, and maximum energy product, especially when we are talking about permanent magnet. So I will explain this with the help of this cartoon, which essentially called a magnetic hysteresis loop. So magnetic hysteresis loop, what happens? So if we are at the origin, so that means we have not applied any magnetic field. And thereafter, when the magnetic field is applied and that the material reaches, please refer the red color loop, the square shaped loop. So when we apply the magnetic field, keep on applying, after some field, there will not be any further increase of magnetization of the material, because all the domains of the material will be oriented or saturated by the time. And then on reversal of the magnetic field, the magnetization will keep decreasing, and at even the field is zero, it will still retain some amount of magnetization, which is called remnant magnetization. And the remnant, to nullify the remnant magnetization, we need to apply some amount of the field in the opposite direction. So when we apply this much field in the opposite direction, then we actually can get rid of this remnant magnetization, and therefore this negative field which is required to nullify this remnant magnetization is called the coercivity of the material. So therefore this is the remnant, that is at H equal to 0, the value of M is called the remnant magnetization. So at the saturation magnetization, and the negative field required to nullify remnant magnetization is coercivity. So as I explained before, that B equal to H plus M, this loop what we are seeing basically is M versus H loop. So you can as well plot B versus H loop too. So now that is shown in the blue plot. And now you can see that from the blue plot, there is one kind of coercivity we get, which is lesser in value. From the red plot, we get another type of coercivity. So the coercivity we get from the red plot is called intrinsic coercivity of the material, and the one which we get from the blue plot is called the coercivity of the material. And there I have listed in the two sides, there are different parameters. Some of them are the intrinsic property, for example, saturation magnetization, anisotropy field, Curie temperature, etc. Whereas there are some other properties like remanence, coercivity, etc. So they are basically microstructure sensitive parameters. So therefore we can engineer them, we can tune them by controlling the microstructure. So this cartoon shows how actually the domain configuration changes. As I told, that when you keep on the magnetization, when we keep on the magnetic field from the zero value, then initially what will happen, the domains which are non-favorable, which is away from the applied field direction, they will try to first rotate themselves to make the entire energy condition minimized or favorable. And after that, some of the domains which have already oriented themselves along the direction of the field, being low energy configuration, they will try to grow at the cost of the other domains. And finally, at the highest field, you can see the entire material will be converted to a single direction domain, or ideally single domain. So that is the theoretical saturation. However, in practice, we cannot realize such. So therefore we realize 90% or 95% of it. So that is called the technical saturation of the material. Well, as I was talking that the magnetic domain, let us see how actually they look like. So this is you can see in a grain oriented silicon steel the configuration of the magnetic domain. The color contrast will actually tells us that the two domains are two opposite direction. And as I was telling, that domain movement mechanism, you can see this cartoon over here, the bottom was right. So what happens that whenever the first thing of course is rotation. So when the magnetic field is keep on getting applied, so some of the domains which will which is actually away from the applied field direction, they will try to rotate themselves to make them favorable condition. And finally what will happen, you see this bottom plot right side, that the domain wall will move. So when you can see that in the two sides across this domain boundary, the spins are oppositely oriented. So therefore, if by application of magnetic field, we can flip some of the spins which is in the right side domain, so that will make that the red color arrows, you can see that is the left side domain is got extended. In this method, the boundary is moving. So as I was talking about the hysteresis loop, we can encounter different type of hysteresis loop. So the one which is having no coercivity, they look like a very thin and of course very tall. They are called the soft magnetic material. So there are two class of soft magnetic material. In some cases, there is almost no coercivity. There will be the milliostat kind of coercivity. So they are called ultra soft magnetic material, and there are certain material where you will see very less coercivity in the less than 10 oersted or so. So those we call soft magnetic material. And then slowly when the coercivity increases, we call it as semi-hard, and finally a big square loop of the M versus H hysteresis. What you see the rightmost plot, they are the characteristic of hard or permanent magnet material. So therefore, this permanent magnet, why they are called permanent? Because once I am sure that all of you have seen a permanent magnet bar either within a toy or some other device or somewhere. You can see that if you leave the magnet for quite a time, so none of the force of attraction, the power of the magnet, it never changes. So therefore, it will permanently or perennially can deliver the flux. Therefore, it is called permanent magnet. However, if we have a solenoid, that is a current carrying conductor, so there the magnetic field goes the moment you switch off the current. So that is called a temporary magnet or electromagnet, whereas the bar what we have seen in the home, that is called permanent magnet. Well, how permanent is the permanent magnet? Let us also understand. So normally the magnet does not lose much, very insignificant amount of magnetism over the time. Of course, in the modern day magnet, we have very strong magnets which are almost lying intact over the time. However, there are certain external influence which can reduce the strength of the magnet. For example, external heat, radiation, and there are strong electrical currents. I mean, another current carrying coil, if you place near a magnet, so if the magnetic field produced by the coil is in the opposite direction of the permanent magnet, so over the time we may lose the magnetic property of a permanent magnet. Now let us unlearn that. Let us learn that what are the application of this permanent magnet material. Well, yeah. So the permanent magnets are there are basically three types of thing. One is that we can use it in different device like automobiles, aircrafts, power generator, etc. And as a thin film, these permanent magnets, they can be used as the memory device, or there are micro actuators or so on, and also the recording media. So automobile, we may not be aware that there are several places where magnet use. The cartoon shown here, schematically shows the different places where the magnets can be used in automobile or being used. For example, we always have the power window option where we pull up and pull down the window. So this power window actually runs by a very small motor where magnet is used. Same is the case for the wiper and many other places, in fact. So in fact, certain sensors, the torque sensors and all, what is used in the car, they also use permanent magnet. So of course, now we all talk about hybrid vehicle, electric vehicle, because green, there are the green concept for the cleaner environment or so. So this, you may be aware that this electric vehicles, there will not be any fuel, it will run by the electric motors. So these electric motors will use very good quality, high grade of permanent magnet capable of maintaining its strength with an operating condition, for example, higher temperature also sometimes, some of the cases. So in fact, this permanent magnet research today is one of the important thing is this hybrid vehicle or electric vehicle. In fact, you can see that there are already certain electric vehicles. We have already seen some buses which is run by the permanent magnet motors. So now I will tell you about a very nice concept. So you have heard of this high TC, that is high superconductor, which are working or remaining superconducting at higher temperature. When actually you bring a superconductor closer to a permanent magnet, what happens? By virtue of its property, superconductor don't allow any magnetic flux through them. So therefore, a superconducting coil, when it is brought very near to a permanent magnet, they will repel each other, with a very large force. And this concept is being used for a very high-speed train called maglev or magnetic levitation trains. You may be heard of that Japan and China, they are running this kind of maglev trains. So another, that's a health sector. The magnets are used in the MRI. The MRI machine has lots of permanent magnets. Nearly 1 to 3 tons of the neodymium iron boron magnets are used in each of the MRI machines, and it is one of the very crucial equipment for several health-related diagnostic purpose. The magnet also are being used to make the pump implant in the heart. For example, there are certain pump implant to be fixed in the heart. There are also this ventricular assist device pump. They use small magnet. The other important use of the magnets in the energy sector, the windmills. The windmills actually, each windmill use nearly 2000 kg of magnets. So, and they produce so much energy, the electricity. Therefore, you can understand that how important the magnet is for this purpose also. And in the defense, we use several missile systems, airborne systems, aircraft systems. There are a lot of actuators or micro actuators are being used, and those actuators, for example, control of the fins, navigation, the tail fin, and all those things, we use small magnets. So there permanent magnets of different grades are being used, and also for the electromagnetic purpose in radars, the traveling wave tubes to generate this microwave, lot of magnets are hard magnets, permanent magnets are being used. So the other some more application is there are some actuators which are used in the naval systems, the naval reactors and the ship propellers, and some of the underwater devices, they actually propels by motor and electricity, and these motors uses a good amount of permanent magnet. And in the space application also, so SM2CO17 types of magnets are being used. One of them is the ion thruster engine. You can see in the picture. So there are many places where these motors are being used, and accordingly, and magnetic bearings are also used because there are high-speed shaft. So you cannot use the regular bearing. So there we use the magnetic bearing so that we can levitate the shaft without any application of friction. Well, I was telling that microwave generation also requires permanent magnet. This is a schematic of a traveling wave tube where the circular magnets are being used, so which will basically guide the electromagnetic wave for production of the electricity used in basically different radars. Well, coming back to the hysteresis loop, where we have introduced the concept of permanent magnet, let us understand what is the figure of merit when you are giving a permanent magnet to some application engineer. There are two things they are looking for when we talk about a permanent magnet. One is the BH max, that is the energy product. I will tell you in the next slide. And the other thing is the coercivity. I told you about what is coercivity. So BH max, basically it is the maximum area of the rectangle which we can inscribe in the second quadrant of this hysteresis loop. Basically, you can see here, you can plot it, that you can multiply B and H and plot it over the H or B. You can find that at certain value there is the maximization of this BH product, and this maximized line is shown by this this slopy line, that PO, and this PO where the BH max, where if I draw one vertical line from this point and one horizontal line, so the area of the rectangle is the maximum energy product, and the line PO is called the load line. Therefore, the magnet, if we are using in application, if we want to derive the maximum benefit, should be used in this condition, that is along this load line. So now let us talk about how the coercivity comes in this permanent magnet material. Essentially, there are two dominant mechanisms what we have observed in the permanent magnet. One is called the nucleation mechanism, the other one is the pinning mechanism. So I will tell you in detail what are they. So nucleation mechanism and pinning mechanism I will talk about in this slide. So pinning means people who are from the material science background, or especially who have studied the mechanical behavior of the material, you may very well know that the dislocations being pinned at different defects, grain boundaries, second phase, and so on. So same is the case with the magnetic domain wall. So magnetic domain wall, they also interact with non-magnetic particle, non-magnetic phases, some other magnetic phases, second phases, grain boundaries, or even defects like dislocation and so on. So therefore, when the domain wall boundary interacts with them, the pinning occurs, and the nucleation means if there is a defect. For example, if you see this plot, so if there is some defects, for example, depression from the surface, or there is an extra material in the surface, a bump over here, and also there are some non-magnetic phases. So they are magnetically soft phases which is present in the material. They are having potential to, so now you are applying applying a magnetic field from outside, opposing the direction of the field what is present inside the magnet. So in this scenario, such defect sites will cause the nucleation of domains. For example, if you see A, B, or C locations in this picture, so these locations we can have domains which is having opposite sign to that of the parent material, and as and when the applied field from the externally will increase in the strength, the size of this reverse domain increase, and they will swallow the parent material and demagnetize it completely, because now they will actually opposing the magnetic field of the parent material. So this way we can lose the property of the magnet, and I told that in case of pinning there will be different boundaries, and depending on the if those defects and boundaries present in the material are comparable in size with that of the magnetic domain boundary, and then we can see this kind of pinning. Okay, so therefore this pinning as well as nucleation, we can see we have talked about different phases, different grain boundaries, and so on, and there lies the role of processing the magnetic material for correct microstructure engineering. Well, if I have been given a magnet with 12 kilogauss field, so I just want to ask you, whether we get 12 kilogauss at all in the application, because if you see that that magnet, when we are keeping in the air and we keep measuring the magnetic field starting from the surface of the magnet, we can see that the magnetic field will decrease drastically. So therefore, if you can see here that 12 kilogauss magnet, NdFeB magnet with 35 energy product grade can give approximately 2500 Gauss field 1.5 meter away, and 2200 Gauss field flux 2.5 millimeter away. Now there are three things which are important over here. One is the shape of the magnet. If I have a very thin disk, I will be losing this magnetic field quite fast away from the surface. Because of the thin shape, there will be a self-remagnetization of the magnet. And if I take a long bar, there will be very minimum self-remagnetization. There I can have a more field close to the surface. Well, now if we see, as we are always talking about the second quadrant curve, you can see that the one which is in the shape of the square, which is at the top, is the M versus H curve, and the slopy line which is shown inside is called the B versus H plot. Now, if the coercivity of the magnet is very less, then this straight line, it will never remain straight and cuts that horizontal axis. So instead of that, if you see the left side picture, so there will be some slope. The line, the linear, the plot will slope down towards the edge, and they will cut the horizontal axis. So if the scenario is like the left side case, then what happens? We don't call this is a good magnet, because every cycle of demagnetization, this magnet will lose its own magnetic strength. So, but we always prefer a magnet which is having very straight linear curve starting from the resonance point till the coercivity, that is the horizontal axis. It should have completely straight. Then only the magnet is called a good magnet. Well, so now there are, starting from the lodestone, when the people realize the magnetism, there are different magnetic material, or especially the permanent magnetic material, they have evolved over the generations. So people first made hard steel, because steel was the only magnetic material known those days. So people have made some deformation processed steel, and then it came ferrites and other magnets, and then we got this transition metal based magnet like alnico and iron chromium cobalt, MnAlC, those grades of magnet. And finally we have reached a stage for the rare earth magnets because of their exotic properties, and from there we are going and in further futuristic evaluation. Well, so I will now briefly describe about different types of magnets, permanent magnets, and how they are made in my subsequent slides. So as I told, the earlier magnets was the alnico magnets. You can see this microstructure. It has got very nicely oriented precipitate. These precipitates are the hard magnetic precipitates, and their shape, that is the elongated shape, that creates that is the source of the coercivity in this alnico material. Alnico material can be made through melting and casting route, or the powders of this material can be processed through die compression and followed by sintering route. So this is the typical magnetization, demagnetization behavior of the alnico magnet. It has got, of course, lower coercivity when we talk about the new generation rare earth permanent magnet, but this was one of the earliest development in this field. And from the alnico magnet were actually processed by melt processing or by PM route. But while the concept of orienting the powder particle was not present at that point. So of late, the researchers learned that, okay, if we can reduce the particle size and make the particles close to single domain, that means each particle will have only one domain. And in this situation, if we can orient these particles by application of external magnetic field, then basically we are orienting all the particles along their easy direction of magnetization. We are orienting them, and in this condition, if you can sinter, if you can compact and make the magnet, you are having a perfect orientation in the magnet. So once this was realized, so first it was applied in case of the ferrite magnet, the hard ferrite. They are basically some class of the iron oxides, and there first the powder were made, they are oriented and then sintered, and then we found that yes, the researchers found that yes, this really improves the efficacy of this kind of permanent magnet material. And you can see this demagnetization curve, and when you compare with the Alnico, you see there is a substantial improvement of the remanence as well as coercivity, and accordingly the energy product is also high. There are the different grades of hard ferrites. So you can see that they have the beer in the range of course, different grade up to 4000 Gauss, and coercivity in the range of 2.5 to 3.5 kilooerstat, and energy product up to 3.5 to 4. And but these magnets can be operated to a temperature of 300 degrees C. Now this plot over here on the left side of this image, it basically shows that how the different class of permanent magnet they evolved over the time. What we can see here, that the highest in this tally is the NdFeB magnet, and of course followed by the other class of rare earth permanent magnets, that is SMCO type of magnet, means SMCO5 or SM2CO17 grade of magnet. So therefore, more than this Alnico or this hard ferrite, this rare earth permanent magnets, they exhibit much better permanent magnetic properties. And why we need more energy product, why we need more beer? So if you see the right hand side plot in this slide, you can see the stronger the magnet, the volume we require to get the similar flux, similar strength, similar efficacy decreases. So stronger the magnets, stronger the magnetic material, smaller the piece required to perform the same function. So therefore, in view of the device miniaturization, the pursuit of the stronger magnet is required. Well, the most of the rare earth permanent magnet. So the rare earth is the lanthanide series, which you can see in the bottom, with the 14 element series in the periodic table, starting from cerium and ending at lutetium. These 14 elements, this rare earth magnet, they are actually the first 7 elements are normally being opted for preparing this rare earth permanent magnet in combination with transition materials such as iron, cobalt, and nickel. But what is the so specialty with this rare earth? Because this rare earth materials, their magnetism stems from the 4f orbital, and the 4f orbital is not delocalized. That means electrons of the 4f orbital are not delocalized into the crystal field, or they are not going into the other crystal field. So therefore, their moments are very much localized, and depending on the number of electrons, number of unpaired electrons available in the 4f shell, they have the magnetic moment also very strong. And the other most important thing of this rare earth material is the spin orbit coupling is very strong in this material. So that means spin talks with the orbit very nicely in this rare earth material, which is very weak in the regular transition materials such as iron, cobalt, nickel. Therefore, if you combine these two, but unfortunately, this rare earth material, their magnetic order is retained only to a lower temperature. At room temperature, most of them are merely paramagnetic. Therefore, but transition metal on the other side, they have very high Curie temperature, and having very high Curie temperature, they are actually magnetic till much above of room temperature. So if we combine these two, if we perform some kind of hybridization between these two, so we can take advantage of high Curie temperature of the transition metal and strong spin orbit coupling for the rare earth metal, and strong spin orbit coupling. Actually, this is very important because now your spins are now tied up or coupled with the orbit. So having coupled, so the magnet will not so easily be demagnetized under the external influence of the negative magnetic field. So that is called a strong magnetocrystalline anisotropy. So all the orbital, they are nicely anisotropically oriented, present in this class of material, and by combining this rare earth and the transition metal, we can tailor make different good qualities or great qualities of the permanent magnet. So even as I told earlier also, that every permanent magnet material, the microstructure, the grain size, the defect, all these things are important, and therefore a nice microstructure engineering approach is required. And this is the formula that computes the coercivity and the BR, that is the remnants of this permanent magnet material. You can see in case of the remnants, a cos phi term appears. This cos phi term says the orientation, how in which crystallographic direction the magnet is oriented. So therefore, a oriented material is required, and also the density, that is shown by rho, and volume fraction of the other non-magnetic phases. So, and coercivity also, again, it also depends on the several such microstructural parameter. So therefore, they are tailor making the microstructure, grain orientation, all these things are very important for processing of permanent magnet. So when we talk about the rare earth permanent magnet, so there are several challenging things, because controlling the chemistry, rare earths are very reactive with the atmosphere. So we have to process under inert atmosphere, and that too we are handling powder metallurgically fine particles. And then we have to apply a good amount of high amount of magnetic field, because I told they are anisotropic, so they need higher magnetic field to flip their domain into the desired direction. So therefore you need very high magnetic field. So creating high magnetic field also is challenging, because you need to pump in lot of current, and more current means more joule heating. So therefore you should have the auxiliary cooling arrangement for this kind of setup. Well, and also as I told that homogeneity in the microstructure also how to maintain, that is important. So I will talk about some issues in the subsequent slide. So let me begin my presentation with this part of the story with 217 type of magnet. You can see this microstructures. There are nice fine precipitate distributed in the cells in the microstructure. So this 217 type magnet, the coercivity comes by interaction of domains with this fine precipitate, which are very, they are all SMCO5 type precipitate. They have strong anisotropy, and thereby they pin this magnetic domain very, very efficiently. And this 217 type magnet, they are also prepared by powder metallurgy route. So the alloy is prepared by vacuum induction melting, followed by we make fine powder using planetary ball mills, and followed by we orient the powder. You see this green color machine is basically a very high power electromagnet, and which basically helps the powder to get oriented in one particular direction. And subsequently this and here in this case we also apply the pressure to make some handleable green compact strength, and apart from that we apply the strong magnetic field to orient the powder. So this oriented green compact, subsequently they are sintered, and then we can fabricate different types of components as shown in this slide. Well, I was talking about the compaction. There are two types of compaction we generally adopt. In the left side one, the magnetic field of the electromagnet and the pressure applied to the powder, they are parallel to each other. Whereas in the right side one, the magnetic field applied and the pressure applied, they are orthogonal to each other. So if we see what is the benefit of the right side machine is that when you apply the pressure will try to destabilize the orientation formed in the material. Whereas if the magnetic field is applied in the direction which is away from the pressure direction, basically by pressure, we are consolidating the orientation achieved by magnetic field. These are the some of the microstructure, and this is called the X-ray pole figure. Basically, it tells that how strongly the material is oriented. So, for example, if in this particular magnet we want that all the material, they must oriented along their c-axis of the crystal. So, when we talk about c-axis pole figure, so if the contours are very close to the origin of the pole figure, so that means the orientation is stronger. If it is having some scatter, some spread, so then the orientation is not very strong. So as I told in the previous slide, that this is the comparison between the two different methods. The left side one made by the transverse press, that means the right side arrangement, and the right side one made by the left side arrangement. So you can see in the right side texture plot, the spread is much more compared to the left side one. So therefore, left side one having better texture. And so, and this particular 217 class of material, we follow a very complex heat treatment because it is having some 5 element system, SMCO, Fe, Cu, and Zr. And here, first, we ensure that every solute is in the solution at 1180 degree or so. We do the solutionizing. Subsequently, we quench the material to retain all the solutes inside the material, and then we do control heat treatment called edging, so that a desired morphology and volume fraction of the strong pinning precipitates they come. So efficacy of this heat treatment is very important. You can see from this slide that we have adopted different heat treatment, and you can see this demagnetization, the second quadrant plot based on the heat treatment, how the plot shape is changing. You can see that in the optimized condition, a plot should like this, which is shown in the bottom left corner. So it should have very much square shape and very linear, that red color demagnetization curve from the BH loop. So therefore, the heat treatment and role of precipitate and the distribution is very important. When in the 217 type of material, we also have another grade of 217, which is called temperature compensated 217. Normally, if we take any permanent magnet material and slowly increase the temperature, its magnetization, that is the remnant, continuously decreases. However, there are some special grade of SM2CO17 class of magnet where the temperature, with respect to the temperature, the magnetic flux, the magnetic field strength can be made constant or can be kept constant at least for a range of temperature. The cartoon showed in the right hand top corner, it shows that based on the nature of the different rare earth, the R2 transition metal 17, R stands for rare earth, R2 transition metal 17 type of compound. In some of the compound, you can see the blue color curve in the top, that magnetization for decreases with temperature. This is the case of the SM2CO17 case. However, if we add some other rare earth, in some cases it is the reverse. That means with temperature, the magnetization increases. And if we can nicely combine these two, it is possible to maintain the magnetic flux constant over a certain temperature range. So we have actually tried two different things. One is that gadolinium addition with samarium. So samarium is replaced partly by gadolinium, because gadolinium 2 GD2 TM17, it has positive slope, whereas SM2 TM17 has negative slope, and therefore when in combination they will, if we can adjust the composition such a way that they can be made constant over a temperature range. In fact, we can compute a parameter called alpha, which shows the temperature coefficient of remanence, means remanence how it is changing with temperature, and we have achieved the remanence as low as something like 60 to 80 ppm. However, we have our research further, and from this 60 ppm of these things, what we can do that we have also added some erbium along with gadolinium. Now this 60 ppm coefficient can be reduced to 25 ppm. So the point I want to drive home from this set of these slides is that the first slide about the normal SM2CO17 grade shows how the heat treatment processing, how the microstructure tailoring precipitates, they are important, and this class of magnets shows you how the composition tailoring is important. So therefore one must take care of this kind of metallurgical processing to get a best quality of magnet. So I won't go detail in this slide. So this shows that with respect to different GD and ER ratio, how these magnetic properties are changing, as well as this alpha. You can see that it is basically also we have to take care that different phases formed with when you change the rare earth, and those kind of optimization studies are important. So now the SM2CO17 normal grade of magnet, they can go maximum, they can be used rather maximum to a temperature of 350 degrees centigrade. However, there are certain high-end applications where these magnets are used in these certain motors which have very high RPM, and there the temperature rise is very high, and in those cases actually we use the ultra high temperature grade 217 magnet. There also composition optimization is important. As I told, this has a 5-element system, so we have to adjust, strike a balance between iron, copper and zirconium along with samarium, and by doing that you can develop a very high temperature grade of magnet. We can see in this plot like that the magnetic properties are measured in different temperatures, and we have in fact by tuning this composition we have developed ultra high temperature magnet which can work at to a temperature up to 550 degree centigrade. Well, all these magnets so far I talked about, that is SM2CO17 class of magnet, they are all pinning type of magnet by virtue of this precipitates form. But as I told earlier, there is another class of magnet which has the nucleation type of mechanism, and neodymium iron boron magnet is one such in this class which has this nucleation kind of demagnetization mechanism. If I look at the typical microstructure, it is a schematic one. For the right side plot, right side cartoon, you can refer that there are two phases. One is Nd2Fe14b, which is white color there, and the matrix phase all around them is neodymium rich phases. And these neodymium rich phases should effectively encircle or wet all of these 214b particles. If it does so, then the 214b particle will not have efficient communication. It is something like yourself and your neighboring house. If there is a very big and strong wall in between, the two neighbors cannot talk to each other so nicely. So the neodymium ray acts as the wall between 214b phase, and this neodymium rich phase basically shields any kind of magnetic interactions between these two 214b phases. Now, why such shielding is required? Because if in one of the particle loses its magnetism due to application of external field in opposite direction, if the channel of communication between two particles is very high, very nice, very strong, then immediately it will influence its neighbor and demagnetize him. However, if the shielding is efficient, even one of them is demagnetized, the effect will not immediately be realized in the neighboring particle, and thereby the material will have very strong coercivity. So this microstructural engineering is also very important, how to create such nice envelope all around the 214b particle. You can see this microstructure. The dark color lines, they are neodymium rich phases, and the inside you have 214b. You can see how nicely they are shielded from each other, and this wall you can make it stronger. For example, between two neighboring house, you can make the wall, make a brick, you can make a wall, make of iron and steel, or make of some kind of very strong stone. So depending on the material you use for the wall, so the wall will be stronger or weaker. So in this class of magnet, the neodymium rich phase, which is the shielding between the 214B phases, you can further strengthen the efficacy of shielding by preferentially diffusing dysprosium into it. You can see here by dysprosium diffusion, the coercivity, how the coercivity increases. When you go from the right to left, you can see the more dysprosium is infused, the coercivity is increases. And you see here also, microstructure is important, number one, and number two, the composition of these phases also important. These plots summarize just alone based on the composition which way the different magnetic properties changes in this class of system. You can see that are the NdFeB magnet like 270 magnet, they are also processed using that powder metallurgy route. But in the neodymium iron boron magnet, what was observed is that the starting material, if is having a desirable microstructure, already this rare earth rich phases circling around the 214B phase, then it is probably beneficial. Accordingly, a method which is used called the strip casting, where extremely high cooling rate is used to quench or solidify the material to get the nice microstructure as shown in this slide. And further, these flakes obtained from this high cooling rate process are used for further PM processing. You can see just by doing that, the energy product can be increased from 34 to 40 energy, 40 megagauss per step. Well, based on the, and there are some other process techniques also. We can use hydrogen also during, compaction and other things. And there are different grades of material. When we look for the material with higher energy product, they will not be so useful at higher temperature. However, the magnets which are useful for the higher temperature, their coercivity is important. You should have very strong coercivity at room temperature. Let the energy product be slightly compromised or less, and those magnets can be used at high temperature. And now the hydrogen is also being used to process this NdFeB. Why the hydrogen is used? Because that hydrogen will actually go into this in ND phases that I show, the shielding phases. So hydrogen goes into those phases, and by doing that, it will basically make that phase very brittle, and accordingly the 214B particles will be standalone and they will break out of it. So you have now nice 214B particles. You can orient them magnetically very nicely and get a very good property. The other nucleation type of magnet is SMCO5 magnet. So they are also basically, the process is similar to 217. So I will not go detail about it. And this magnet is also basically processed through powder metallurgy technique. And you can see that there also we get, but of course we don't get the energy product as high as the 217. However, we get reasonably good energy product of 15 to 18 megagauss per state in the SMCO5 magnet. And this SMCO5 magnet, we wanted to improve further its property, and accordingly PR has been used, and by doing so we could increase the energy product up to 24 megagauss per state, which is remarkable in this class of system. And here also you see the reason for the high magnetic energy product in this PR added system also stems from the microstructural engineering. We could form some 2,7 type of phases, which is also present between two SMCO5 particle, and they actually having very good shielding strength. They shields between two particles, and accordingly the magnetic energy product is good. So this magnets, what we are showing here, PM route and all, basically they can make the scale of operation is very small, and that is up to say half kg or maximum at the scale of 1 kg. Therefore, in DMRA, since we are working for the larger systems, we need to develop a larger magnet. So accordingly, we have innovated a different process route. So here we have used a technique called cold isostatic pressing. So there we pour the powder into this rubber mold, and the rubber molds will be completely sealed with different mechanisms, and after sealing they will be put into a water tank, and in the water tank we will apply very high pressure to compact it from all directions uniformly, and this is then actually processed by heat treatment and other route. In this method you can make a very large magnet. In fact, we have developed different magnets in this process. However, I have my point of showing, the point I want to drive home is that here also, if I compare a magnet which is processed through the conventional PM route, which is left side, a magnet which is processed through the cold isostatic pressing route, which is shown in the right side. Now, if you compare these two plot, you see in the right side plot, you have less coercivity. However, it has higher beer and more energy product. Whereas in the left side plot, we have more coercivity, but lower beer and lower energy product. So we wanted to investigate what is the reason. Again, we have resorted to X-ray pole figure technique. You can see the cold isostatically, that is called CIP sample. The orientations are very tightly spread around the origin. So therefore, it has more orientation. If you connect this fact with the equation I shown before, that the more orientation, stronger orientation means you have stronger magnet, stronger beer. Accordingly, the CIP sample has more beer. And TP, that is the conventionally processed magnet, it has some spread, therefore it has the less beer. And this is the orientation also you can see in microstructure. So I will not go into detail. And this is the precipitates, the pinning precipitates formed in the 217 type system. And here actually from the transmission electron micrograph, we can also find out the distribution of element. You can see that in the precipitate phase, there are more coppers but less iron, whereas in the matrix phase, I don't know in this magnification whether you are able to see because it's not going to full screen. However, we can, I tell you that this precipitate phase has more copper and less iron, and the matrix phase has less copper but more iron. But then this precipitate wall width is different in two different samples. A conventionally processed material has a very thinner width, a SIP processed material has a wider width. So when we see how the anisotropy varies with the copper concentration, we find that the wall anisotropy is actually increases with the copper enrichment. So therefore, when you have the wider width, so the pinning field is actually very diffuse. So that means in a wider width, I have copper gradient from one edge to center, and then it is decreasing. And therefore, what happens that the pinning is not very efficient. Whereas conventionally processed magnet, the precipitate width is very thin, and there you have a very sharp distribution of copper, and pinning field is very strong. So another method we found that we can do these things even using some vacuum packing. So there is no restriction with shape, no restriction with size. So unrestrictedly we can increase the scale of operation. All these magnets are also having, like they are reactive because the rare earth has reactivity. So we have developed some coating also for this magnet. These nickel, copper, nickel tri-layer coatings are very efficient to protect these magnets from this environment. So this is we are ready with the upscale magnet. Now, how do you select a magnet for a typical application? So briefly, I have covered that we should know first the dimension of the magnet, and after knowing the dimension, we know that in this y-axis where actually the magnet lies, and then we have to see that from this BH loop the magnet product line, and then we can design a magnet such a way that the shape and the thickness is such a way that it's after demagnetization tally with this horizontal line. So this is the consideration of designing a magnet. After that, we have to do lot of measurement, we measure the BH loop measurement and also its intrinsic, and also the magnet. Once you make a particular shape, you cannot put it under BH loop. And how will you characterize? So there, what we use, that there is a probe called that probe is known as the Hall probe, which is cylindrical type. So you touch that probe on the surface of a machine magnet, and you will know like what is the field it gives at a particular distance from the surface. Well, rare earth magnets, which is kind of the magnets of present. However, we have to go beyond. We have to go beyond the, this is kind of rare earth magnet field is kind of getting saturated. Look for more innovative approach and newer material, and therefore the one such concept is the exchange coupled nanocomposite magnet. In the exchange coupled nanocomposite magnet, let me briefly explain that the left side plot is the soft magnet. It has a low coercivity but good BR, whereas the middle plot is a purely hard magnet. It has low BR but high coercivity. What if I can bring these two together, and after bringing these two together, I will be able to take the advantage of the high coercivity of the hard magnet and the high BR of the soft magnet. But if the marriage is not performed, the coupling is not performed very properly, you will have a step in the curve. Of course, if you can couple them properly, that you can have a loop with the tall height, that is higher BR, as well as wide, that is having higher coercivity. So, so such concept can be possible in the nanocomposite magnet. In the nanocomposite magnet, I don't go detail of this slide, because there we need to tailor make, basically the soft magnetic phase of a particular size should be made embedded into the hard magnetic matrix, and the soft magnetic matrix should have cannot be very coarse or should not be very fine. So there is a size limit for that. So we can do it either using by particulate method. We can prepare the particular size of this soft phase and then mix them, do the milling, and we can mix them nicely in the with the hard magnetic powder. And you can see this is one such example where SMCO-Cu magnet, that is 1,5 type magnet, was hybrided with the iron nanoparticle, and there we can see that based on the mixing ratio and all, how the loop is changing actually, and how the loop is becoming more thicker, I mean fatter and taller. Now the same thing can be made by growing multilayers. This is a multilayer of SMCO5 and iron. So when the multilayers are grown one after other, then also we can realize magnet which is having, for example, no SMCO5 magnet in the bulk condition, in the PM process condition, can give us 31 megagauss Oersted energy product. However, in this concept, the magnet with 31 megagauss Oersted can be produced. Well, that is the approach wise what we can do further. However, there is also requirement of making rare earth free permanent magnet, because I must apprise you that the rare earth element, 85% of the reserve, global reserve, so that is available with China. So therefore, it is a Chinese monopoly which is in the rare earth market. If they decide, they can give us. If they want to withdraw the permission, they can stop also. So the entire world is doing research on how to come out with the alternatives where there is no rare earth in the magnet. So therefore, in the recent situation, that this activity particular has gathered much more thrust, and the several rare earth free permanent magnet are being explored. In DMRL, we have studied two such permanent magnets. One is zirconium cobalt based, and other one is hafnium cobalt based. So we have done some initial research on this classes of permanent magnet. In the zirconium cobalt, we have tried to do certain substitution, elemental substitution like copper, niobium, silicon, and so on. With this, we could get maximum energy product of nearly 3 megagauss Oersted, and the coercivity up to 5 kilo Oersted. And these are the transmission micrograph of these Z ribbons basically in this material to suppress, because if you see the phase diagram here, the phase which is responsible for hard magnetic property, it is a high temperature phase, and therefore to stabilize them we have to carry out the non-equilibrium solidification processing such as melt spinning and so on. These are the microstructure for them. And again there also microstructural study is important. The other one what we are working here is the hafnium cobalt based system. In hafnium cobalt based system, the permanent magnetic phase is HFCO7 type intermetallic, which is again high temperature phase. Therefore melt spinning technique was adopted, and by melt spinning we could stabilize. First of all, actually we studied across the composition range and identified the proper composition range, and then melt spinning was carried out. By melt spinning we could improve the coercivity, but however the melt spin ribbons are very small inside. How to make a bulk magnet? The usable magnets are the bulk magnet, a compact disc, or at least a disc. So therefore what we did, this ribbons whatever we made, in the ribbons we get also very good property. In fact we get 8 megagauss Oersted, which is the highest achieved property so far in this system. But these melt spin ribbons you cannot make powder, they are very ductile, very difficult to crush. So therefore we have adopted a technique called cryomilling. By doing cryomilling we could make powder of this material, and this powder finally was compacted using spark plasma sintering technique, and by this method we could successfully prepare a bulk magnet. And this is the first ever attempt to make or report to make this bulk magnet. In the bulk magnet itself we realized 6 megagauss Oersted energy product, which around 3 kilo Oersted coercivity. However, this research on this rare earth free permanent magnet is very nascent stage. There is a long way to go. We are nowhere when we compare with the rare earth permanent magnet. Rare earth permanent magnets we have 30 to SM2CO17 30 megagauss Oersted energy product. NDFEB has gone up to 50 plus megagauss Oersted energy product. So we are nowhere there, but theoretically all of them has potential, because theoretically they have been evaluated and it was found that both the system has potential to deliver up to 35 megagauss Oersted energy product magnet. However, it is up to us how to do process engineering, microstructural engineering, and to realize a good magnet out of this system. So the future for the permanent magnet lies in the nano composite magnet, rare earth limb magnet, and also maybe this 3D printing methodologies which is being researched and being evolved. So here some modification with some engineering marvel, we can basically print micron by micron, phase by phase, and such a way we can tailor make some very nice microstructural architecture and thereby a good futuristic permanent magnet. Also the other method what is coming up in the future, chemically synthesized self-assembled exchange coupled magnet. So from fundamentals to applied science to engineering, magnetism and permanent magnets are very important, and magnetism is essential. Especially you have seen how many of the critical system the permanent magnet is being used. So therefore a lot of research has to go in to evolve newer and different materials. So I would like to finish my presentation that with this nice cartoon which show organic molecules as a permanent magnet. Maybe one day will come where we can basically add or tune molecules and make a nice permanent magnet out of it, and it can be made as small as we desire. So with this I finish my lecture, and I'd like to thank DRDO for the financial support and director for his encouragement and permission to do this work, and also Dr. Kamath for his guidance, and our head of our group, and of course our other team members. Some of the results are actually I have taken from their work also. I think we have a very good permanent magnet team at DMRL. We are working for different grades of magnet, and of course the foundation stone was laid by our erstwhile scientists in this group, and I am also thankful to them. and different other groups of DMRL for several other microstructural characterization and processing. Some of the work has been done at Germany in the Professor Hans group, so I am also thankful to them. And thanks the organizer and Mathrusri Engineering College for giving me the opportunity to share our work, our understanding with a large gathering of the students. So thank you all of you for your patient hearing.
Thank you, sir. Thank you very much. Pawan,
Sir, yes, sir.
any questions from the students?
I request the students, if you have any doubts, you can unmute and ask, or you can post in the chat box. Sir Mithun, sir, I have a doubt, sir.
Yeah.
Sir, cryo cooling means up to what low temperature we have to take that material?
Actually, in this the cryo milling you are talking, right?
Yes, sir.
Yeah. So basically, we don't control the temperature. It will have a valve with a double wall chamber. So within the double wall, the liquid nitrogen will be actually circulated.
Okay.
So liquid nitrogen goes into the vowel wall and maintain a low temperature, and in that condition the vowel will be given different motion. So in this process the material will crush amongst each other and they will form fine powder, because at low temperature normally metallic material behaves very brittle. So when you bring them such a cryo temperature, of course it will be above the liquid nitrogen temperature, we don't control them, and at that temperature they will be so brittle that when they crush amongst each other, so they will form nice fine powder actually.
Okay,
But
sir.
we don't control the temperature per se.
Okay.
Sir, one more doubt, sir. The interesting thing is the temperature compensated magnetism, right? So that is what is the range of the temperature, sir, during which there will not be any effect on the magnetism?
Yeah, actually this particular magnet what I have shown, so they are from -80° to +120°. In that range the magnetic field will remain constant, the flux will remain constant in this.
So during the temperature there will not be any effect on the magnetism.
Very minimal. So
Okay,
that is
very
what
minimum. Yeah.
we have achieved the 25 to 30 ppm. So you can understand that small fraction, such a tiny fraction change will be there.
Yeah, excellent, sir. Excellent, right.
Yeah, that property is really amazing, sir.
Yeah, exactly, right. That is very interesting, sir. Yeah.
Sir, this last slide regarding this organic magnetic materials.
Yeah.
Sir, is there any group in our DMRL working on these materials?
We are not working at DMRL because we are primarily on the rare earth permanent magnet and other permanent magnet.
Okay, sir.
But however, I mean, there are reports. Okay, there are reports. You can see some recent issues of this CS Nano. I have seen reports that they are molecular magnets. Of course, so far it has been made only in the laboratory. I mean, nobody has thought about how to, make in reality. And most of the work so far reported is on the simulation scale. Like people are, taking different molecules and performing simulations to predict their magnetic properties. And few synthesis work, of course. But I mean, really lot to be done actually. It's a very immature stage, I would say, this field.
Okay, sir.
Sir, are we in a position to export the magnets to other countries that are being manufactured in the?
The thing is that our internal requirement itself is so huge.
Right. Okay.
So thing is, right now I will just, since you are talking about this export.
Right.
So there are two major grade of rare earth permanent magnet. One is that SM2CO17 or SMCO5. The other one is neodymium iron boron.
Okay.
So samarium cobalt magnet is normally used in strategic sector, that is defense, space, atomic energy. So there we are self-sufficient. We are DMRL. In fact, based on DMRL technology. One plant is coming at a Vizag, so which is now in the construction stage. So they will take care of the entire strategic sector actually. These three sector.
Okay.
However, neodymium iron boron magnet is in the commercial sector, automobiles, for example, with many other places. So there the volume is huge. So DMRL being a research lab, we don't have such facility to upscale such a huge level. And the other major problem is that neodymium comes from China.
Okay.
In the country, we don't have any neodymium resources.
Right.
So neodymium we comes from China, and China has supplied this. They sell neodymium in much cheaper. They sell neodymium.
Chandrasekhar sir, kindly mute your mic, please.
So
Chandrasekhar sir, there is a lot of disturbance.
So neodymium, China sells the elemental neodymium in much costlier rate than the neodymium iron boron magnet. So meaning, if you purchase the neodymium from them and process the magnet, your cost will be much higher than the magnet you get from China, because we are dependent on them for the resources. So therefore, the commercial sector was importing neodymium iron boron magnet from China so far. However, now Niti Aayog has taken a step to make India self-sufficient in the rare earth neodymium iron boron magnet. So therefore, IREL has lot of neodymium oxides they grade when they excavate different materials. So this neodymium oxide, so Niti Aayog is now putting together different agencies so that the neodymium can be extracted in the country and DMRL technology can be used to make a magnet. So this is the current program which is going on, so that we are not dependent on the raw material from China actually.
Right. Thank you, sir. It is really excellent, and it will definitely help us in enriching our knowledge in magnetism. Right, sir. And now, Pawan,
sir, we have two questions from the, sir. We have two questions from the students.
Right. Okay.
Will the permanent magnet will ever lose their magnetism?
No, I told you that permanent magnet will be perennial in general, unless you do something with them. You expose to very high temperature, you bring a electrical coil which is having a fluctuating electrical signal, when that means that it will produce some opposing magnetic field, or you put lot of deformation, that is you are beating the magnet very hard so that the magnets get deformed. So if you are not doing any such thing, normally permanent magnet will not lose its magnetic strength.
Okay, sir. Thank you, sir. Sir, and another question: magnetic levitation trains, should we have to maintain the critical temperature of the superconductor?
Yes, that is why high TC superconductors are being thought of, which is having very close to room temperature.
So we have to maintain the temperature, which should be below critical temperature.
Yes, of course, we have to.
Sir, and another question: can ECE students work in DRDO after graduation if they have interest to become a scientist?
Yes, of course. You can apply for this DRDO entrance exam. And ECE, we have a lot of requirements. Not only DMRL. There are many labs, 52 labs in DRDO, and many of them are electronic laboratory. They do a lot of electronics work and communication work. So therefore, you please go through our website and look for the advertisement, and there will be, now there is a no written exam. It is based on the GATE score actually. And after, based on the GATE score, there will be interview selection, and interviews will be conducted, and you can of course get a chance to work. Yeah.
And some of our final year students are interested in doing project work in the laboratories like DRO, DMRL, and
Of course we entertain. We entertain that. I think Pawan knows about it. Many students comes and they do their.
What is the procedure actually, sir? What they should follow?
So basically, you have to write to our HR.
Okay.
So maybe I will share the HRD email ID with Pawan. So you can,
sure, sir. Sure. Okay.
So once you write to the HR, so HR will basically look for that where are some vacancies are there, and some interns can work, or scientists are interested to take some students for this kind of stuff. and then it can be worked out.
Right. Okay. Okay, sir. Rohan, any?
Yes, sir. There are no further questions, sir.
Right, sir. Right. Now, I request Mr. Chandrasekhar, Assistant Professor of Physics, to just say the vote of thanks, propose vote of thanks. Chandrasekhar?
Uh, Thank you, sir. See, yes.
Right.
Good afternoon, everyone. Yeah, sir. Thank you, sir.
Right.
Good afternoon, everyone. So it is really great that this one, the webinar has turned out to be very successful. On behalf of Matrusri Engineering College, I am Chandrasekhar, Assistant Professor of Physics, Sciences and Humanities. I would like to propose thanks to those who have directly and indirectly contributed to this webinar on materials for defense application. At the outset, I would like to thank our speaker and resource person, Dr. Mithun Palit, who shared his precious knowledge with all of us today. So we are really enlightened by your knowledge and presence, sir. I really liked the way Dr. Mithun Palit highlighted the for permanent bag they are being used in, see, like electrical vehicles and cars and in medical fields such as MRI and in windmills and also in aircraft and like missiles. Okay, and so we see, and like actually, sir, it was really very informative and amazing. Thank you, sir, for your valuable time. We are thankful to our Honorable Chairman, Dr. K.P. Srinivasrao Garu, for his encouragement and support in all our endeavors. I would like to thank our beloved Principal, Dr. D. Hanumantrao Garu, for his acceptance and guidance in conducting this webinar. I would also like to extend my heartfelt thanks to our HOD, Dr. T. Shekharam Garu, for his enthusiastic leadership. A special thanks to the coordinator and the teaching and non-teaching staff for their unflinching support and coordination. Last but not least, a sincere thanks to all the students and participants. With these warm wishes, we officially come to end of this webinar. Thank you.
Thank you, sir, Mithun sir, and we will be in touch with you. Definitely, we will approach you, sir, for any help which will be useful to our student. Definitely, we will come to you, and we need your support and help, sir.
Sure.
In future. Right, and our Pavan, Assistant Professor of Physics, will be in touch with you. Right. Thank you very much, sir. Thank you for sparing your time to be with us today. Though it is Sunday, actually the only one holiday that you usually get. Right. So, and we are grateful and we're thankful to you, sir, for being with us, for spending your valuable time on an important holiday that is Sunday. Right. Thank you very much. Thank you, sir.
I thank all of you for giving me this opportunity, and also the occasion is very great, that Science Day. So I feel
right.
I feel
Yes,
very.
It will be more memorable, sir. It will be more memorable.
Yeah, it is. Yeah, that's the reason we have conducted this on 28th only, sir. We wanted to conduct it, though it is the Sunday. We wanted to have it on Sunday, on 28th. Because most of the institutions, organizations, they have conducted already yesterday, and some are planning to have such programs on Monday. But our college actually wanted to have this program to be held on 28th itself, because it is National Science Day, right? That is. So,
Mithun sir, thank you, sir. Thank you so much, sir, for accepting our invitation. So, thanks from my side personally and on behalf of our organization also. Thank you so much, sir.
yeah, for accepting our invitation.
Yes, sir.
Thank you very much, sir.
Yeah. Thank you, sir. Thank you. I will be in touch with you, sir. Thank you.
Sure.
Yes, sir. I request all the students. I will send you a feedback link. So please fill it and submit.
Yes, yes.
Okay. Thank you, sir. Thank you.
Thank you. Thank you, sir.
With your permission, may I leave now?
Yeah.
Yes, sir. Yes,
Thank
sir.
you very
Thank
much,
sir.
sir. Thank you very much. Right.